Hello and welcome to another video. In this video, we're going to be working on using a robot to print a lexicographically small string. And this one, you're given a string S and a robot, and the robot holds a string, and you have an output string. So you have like three strings. You have the current string, you have a robot string, and you have an output string. And you can do two operations. You can either remove the first character of the string you're at and give it to the robot and add it to the end, or you can remove the last character from the robot and put it in your output. And you want to return the lexicographically small string that can be written. So here, for example, this S is ZZA, the robot is nothing, and the output is nothing. So what we're going to want to do here is, right now the only operation we can do is this. Then the next operation we want to do is this. The next operation we want to do is this. And then we just want to keep popping from the robot to the result. So it'll go like that. So this is our best is AZZ. And then in the second example, we have BAC. So once again, the only thing you can do is this. Then the best operation is this. Then the best is this. Then the best is this. And then this and this. So you get ABC. And in the last one, it's BDDA. So BDDA. So in the beginning, you can only do this. Then, so it's better to just put the whole string on, because essentially this is kind of what they're showing you in these examples is we're able to take any character of the string that we have remaining and put it into like the next index in the output. We're not able to guarantee the rest, but we are able to guarantee like the smallest one we have remaining. And so we definitely always want to have the smallest character in the string be in the beginning of the output. And so basically we're adding to the robot until we get to that character, and then we can put that on. So this is our answer. And you can't just keep track of like the next, like for every element, you can't just keep track of like the min element remaining or something like that after, or like the smallest element after that. So let's take a look at this example as to why you can't just keep track of like what's the smallest character after your current character. And what would that look like, by the way? So like this Y would point here, this D would point nowhere, this E would point nowhere, this V would point here, and so on and so on. So what would happen here is we're going to pop the B and put it in our result right there. Actually, I think I just copy it. So we're going to pop the B and put it in our result. It's going to go like straight off the robot, and then we're going to put the Y on the stack or the robot. And then we're going to put the D. So I guess we can get rid of these arrows. And we're going to put the D, whoops, get rid of these two over here. Or actually, this is kind of dumb. Okay, get rid of that and put this over here. And then, so this D has nothing smaller. So we're going to get rid of the D and put it over here. And now the smallest character after the Y was the D. So we might think like, well, the smallest character after the Y is gone, so maybe we can put the Y on, but there are still small characters remaining. So you can basically have examples like that where, you know, you have like Z, A, B, C, and you can't put the Z on until you get rid of like all of these. So that's why that approach doesn't really work. So let's kind of go back to our original string and then show like what actually does work. So let's get rid of this. So what does work, and this is common in a lot of problems, is storing character counts. And so we can basically store character counts of everything in an array, pre-compute ahead of time. And then when we pop off a letter and put it on the robot, we can use a stack for the robot and just only pop off the robot until there's nothing remaining in the string left over. So let's kind of walk through what that solution would look like. So first we get character counts. Imagine we have character counts of all of these letters. So then we're going to put the B over here on the robot, and we're going to check, okay, so in our character counts of all of these letters remaining, is there a letter smaller? And character counts is only 26, right? So it's very small space. So is there a letter smaller than B? No, there's not, which means B is safe to put in the output now. So we're going to put the B in the output. And then we're going to put the Y over here. And we're going to say, okay, for this Y, is there a letter smaller than Y in our output? Just by using the character counts. Yes, there is. So we can't get rid of it yet. Then we're gonna do the same with the D. So we're gonna say, okay, let's take this D and put it over here. Make this smaller to make it easier to see. So for this D, is there a letter smaller in our output? No, there's not. So we could put this in the result right away. And then we'll check the Y again. Is there a letter smaller than Y? Yes. And then the E. Is there a letter smaller than E? No. So we can put it in a result. So essentially, we're basically saying for the next letter, we can use any letter in here or our stack, or like the top of our stack. And so if there's any letter in here smaller than the top of our stack, we're going to keep putting letters in here. So essentially what's going to happen is we're going to put the V in here, and then we're going to put the F in here. And now there's nothing smaller than F, so we're going to put the F over here. And then we're going to put the Z and the I, and there's nothing smaller than I. So we're going to put the I over here. And now for the Y, we're going to, or actually, yeah, the Y is still smaller than Z. And now we have no string, so we'll just put the robot stuff in backwards from there. So Y, Z, V, Y. And that's our answer. So essentially what we're doing is we have to take a letter every time. And when we take a letter, we're going to check in our robot going backwards, is there any letter in the character counts remaining that's smaller than our letter? If not, we'll pop. So you're using like a stack and just greedily trying to fill out the letter with like the biggest, the smallest character, and you're using character counts to quickly traverse what you have left over instead of the entire array. So we can condense it down basically from like n squared to 26 times n. So let's take a look at that. So here it is. So essentially we get character counts of every letter, and we just normalized by subtracting a. So like a would be 0, b would be 1, and so on. Then we have the result and the stack. So the result is the output, and the stack is like the robot. Then we're going to go through all the characters, and we're going to get the character. We're going to reduce its count. We're going to add it to the robot. And while the top of the stack doesn't have a smaller character, so we're going to get the top of the stack. We're going to check every count. And we're going to check every count. Like, so let's say our letter is like index 10. We're going to check every index less than 10 and see, is there a count there? And if it is, there is a smaller character remaining. So we don't want to pop off that character off the stack. We just want to stop popping immediately and just get the next character. And while we are able to pop, we just keep popping as much as we can. And then we pop and we append to our result and we delete it from the stack. And then finally, we just have like a string builder that we do a toString. And so this should work. It's pretty efficient. And yeah, so the time here, basically what we're doing is for every character on the stack, we're looping through 26 characters. So technically, like the best way to phrase these time complexities is like the number of unique characters in my string times the length of the string is the time complexity. Because who knows, there might be like 300 or 500 or whatever. But in this case, there's only 26, so it's very small. And space is O(n) because worst case we have our entire string on the result. Like imagine, or sorry, on the robot, like imagine you have like this. This is your string with like an A at the end. You're basically going to put all these Z's on the stack. So yeah. But yeah, this does work, works pretty well. So yeah. So the main takeaway here is when you are able to use character counts, try to do that, because that's almost like, for these constraints they give you, this is almost like O(1), that it's only lowercase or lowercase and uppercase or whatever it is. Like using this is basically O(1) runtime. So try to take advantage of that instead of like going through strings. So character counts is like very useful. You can do like sliding window of character counts or whatever other stuff. And it doesn't really cost you anything. So yeah, hopefully this is helpful. If it was, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.